Hi, good evening. Welcome to GD50 Lecture 4. This is Super Mario Brothers. As seen on the slides here, though, we're not using the actual Super Mario Brothers sprite sheet. This is sort of like a rip-off, but I found a really awesome sprite sheet that has all the basic tiles that we need to get this thing working. There's a link in the distro as to where you can find it online. I had a lot of fun playing with it, so hopefully, maybe if you're curious, you can use some of the sprites in there to go off and do your own thing. But Super Mario Brothers, the actual game, which this lecture and assignment are based off of, is the game shown here. I think everybody knows what it is. It's probably the most famous game of all time. But this game came out in 1985, sort of revolutionized the gaming industry. It was the game that brought sort of the gaming industry from a crash in the 70s, thanks to a lot of sort of poor game-making policies and companies and low QA standards. It basically took the gaming crash of the late 70s, early 80s, and brought games really back to the forefront of people's consciousness. This and games like Legend of Zelda and a lot of other NES titles made Nintendo basically the dominator of the video games industry in the 80s and 90s. And even today, with games like Breath of the Wild, they're still doing their thing. But this is Super Mario Brothers. It's a 2D platformer, and what this basically means is you control Mario, who's a plumber. He goes around, walks from sort of looking at him from the side. He walks left to right. He can jump up and down. He's affected by gravity. He can hit blocks. He can jump on enemies. He can go down pipes, and there's like a bunch of levels. It was, for its time, quite a complicated game, and it spawned numerous sort of offshoots and rip-offs and other good quality platformers. While we talk about Super Mario Brothers today, some of the topics we'll actually be talking about are tile maps, so how we can take basically a series of numbers, IDs, tile IDs, and turn that into a game world. As you can see here, the game is sort of broken up into blocks of 16 by 16 tiles. You can see the bricks and the question mark blocks, and the pipes are even all composed of simple tiles, and they map to IDs. And when you take a 2D table or array and you just iterate over all of it and render the appropriate tile at the appropriate XY, you get the appearance of existing in some game world, even though it's just composed of a bunch of tiny little blocks. 2D animation is something we'll talk about. So far, we haven't really done any animation at all in terms of at least characters. We'll do that with Mario. He'll have our version of Mario, an alien. When he's moving, he'll have 2 frames of animation. The frames of animation, it's sort of like a flip book, if you've ever used one, where you can see individual pictures, and when you display them rapidly back to back, you get the sort of appearance of animation. We'll be talking about that. Procedural level generation, we'll be making all of our levels generate randomly, so every time we play the game from the beginning, everything will be completely different. We don't have to hard code a finite set of levels. Everything will be dynamic and also interesting, in my opinion. We'll talk about sort of the basics of platformer physics and how we can apply that to our game world here, because we are just using a 2D tile or a table of tiles, each with an XY that's sort of hard-coded in the game world space. All we have to really do is take an XY of Mario, for example, and then just divide that by the tile size, and then we get basically what tile that is in our array at that point in the world. And so it's really easy to do sort of arbitrary collision detection on, based on what direction you're going, and not have to iterate over every single tile in your world, because it's just a simple mathematical operation to get at the exact tile given 2 coordinates, since the world is in a fixed space. We'll have a little snail in our game that walks around and does a couple of random animations, and we'll go after the player, sort of like a little basic intro to AI. And then lastly, we'll touch on things like power-ups and game objects, and how we might be able to influence Mario and pick those up, and that sort of thing. So first, though, a demo. So if anybody willing to come up on stage to test out my sort of implementation of Mario, that would be awesome. James, yeah, great. I'm going to go ahead into here. So we should be all ready to go. So as soon as you're ready, go ahead and hit return there. Okay. And you should be up and running. So, oh, yep, that's a part of having random levels. So currently, we have a green alien. The blocks have a random chance, in this case, to spawn a gem. And so once they do, you can pick the gem up. Either they have a gem or they don't. You can pick it up and you get 100 points. As we can see, the world is sort of shifting based on where James's avatar is. So it tracks the camera, or tracks the character. We have some notion of a camera. We're getting unlucky with the blocks so far. So you can fall down through the spaces. So So we probably want to avoid that. But if you do, if you want to demonstrate doing it, so in that case, we collided with the 2 blocks below it. The one on the right had the gem. So we go ahead and just fall down so we can demonstrate. So when we fall down, we detect whether the player has gone below the sort of world limit, and then we start them back at the beginning of the game. If you press enter, it should regenerate a brand new world. Notice how we have sort of random holes in the ground. We have random tiles. We have random toppers for them. All the blocks are random. We have snails now. They're sort of chasing after James. He can jump on top of them. There's a lot of little moving pieces here, but a lot of them are actually pretty simple, and I'll show you very, very shortly. So. Yeah, sure, that'd be a great point. So thanks, James, appreciate it. Currently, there is no notion of a level ending. That's part of the piece that actually will be spawn an object that the player can interact with to just sort of re-trigger a new level, basically. But the whole sort of engine behind this basic platformer is there, and it all works. And so our goal is seen here. We want our goal in this lecture sort of is to demonstrate how we can get things like a character that moves around the screen, and a camera that tracks their position, and tiles that are randomized, and maybe there are pillars in the ground, holes in the ground. All of this, again, recall is, at least the tiles are stored as just numbers, so all we really need to do is perform a transformation on a series of numbers. Maybe 1 is equal to a tile being there, 0 is equal to empty space. And so, just by looking at it, we'll see we go column by column. We can say, oh, maybe there's a chance to not spawn any tiles along the Y column on this X of the world map, or on this particular Y, maybe instead of spawning the ground level, we spawn a couple above it and down so that we get a pillar, and so on and so forth. And it's just sort of this sort of summation of these randomizations equals a nice little variety of game levels. So the first thing we should talk about, really, is what a tile map is. And what I've alluded to so far is you can really think of a tile map as being effectively a 2D array or a table of numbers. And it's a little more complicated than that depending on how complex your platformer is, because some numbers are equal to tiles that are solid or not. So you should be able to check whether a tile is collidable, meaning that the player or whatever entity you want to check for can actually collide with it or not. So obviously we don't want to trigger a collision on empty tiles. We want the player to sort of move freely through those. But if they run up against a wall, or if gravity is affecting them and they hit tiles below them or above them, we want to detect a collision and then stop them based on which direction they're moving. And depending on how complicated you get with your platformer, maybe you have animated tiles, for instance. So if a tile's animated, it'll display a different frame of animation based on what timer you're on. Really, the sky's the limit. In this case, we'll be fairly simple. Our tiles will mostly just be numbers with a couple of other traits, which we'll see later on. And this is just an example here of a very simple map, just a colored background. We have our character, and then we can sort of visualize all of those tiles as being, just for the sake of theory, zeros or ones. Yeah, so tile 0. So I'll actually get into a little bit of implementation here as to how we can get drawing some very simple tiles. So if you're looking at the distro, in tiles 0 is going to be where we start off here. And I'm just going to go ahead and run tile 0 so we can see what that looks like. So this is just tile 0. It's a much simpler program than what we just saw. But all we're doing here is just a color in the background and then tiles. So off the gate, anybody have any ideas as to like what the first step would be if we wanted to sort of implement this?
Just put the tiles in a loop, draw them, and then have a background?
So put the tiles in a loop, draw them, and then have a background. Yes, so basically, if this is main.lua in our tile 0, first thing we're going to need is a tiles table to store our, we're not going to be storing just flat numbers. We'll be storing little mini tables that have a number in them, an ID, so we can say tile.id if we have a 2D sort of table. Here we have an empty table, which we're going to populate that. We have, well, we're also going to need, if we're going to draw our tiles, we're going to need a sprite of some kind. And what I did was I just chopped out a little segment here. So this is tiles.png. It's just literally a one tile from the sprite sheet, the main sprite sheet that comes with the distro. And then a sort of on the right side is just transparent so that we can sort of offset maybe tile ID 1 is equal to solid block, and then tile ID 2 is equal to empty. And so if we recall generate quads, we can split up a sprite sheet into however many quads we want to. Let's say this is 16 tiles tall, each tile, and then the whole thing is 2 pixels wide, or 2 tiles wide, so it needs to be split into 2 separate tiles. We'll just generate quads, and then we'll have, recall, a table. Each of the indexes of that table will be a quad that maps to one of these tiles. So number 1 will be this tile here. Number 2 will be the transparent bit over here. And then that's how effectively our IDs are going to map into what gets drawn onto the screen. The ID is the index into our quad table. So going back into tile 0, we have here just a map width and height. We're just going to say generate a map 20 by 20. RGB, we're just going to make it random. So we're going to clear the screen with a random color. And then this is the sort of the quads equals generate quads. And notice that we're passing in tile size here. It's good practice just to make your tile size a constant. So our tile size in this entire lecture, they're all going to be 16 by 16. And so since they're symmetrical, we just pass in tile size. And then here is where we actually end up spawning the map. So nested for loop, y gets 1 to map height, x gets 1 to map width. Just insert, remember, we have to insert a blank table into the base table that's going to act as our current row. And then in that row, we're just going to add a small at tiles y, because y is going to be up here, our current row, an ID. And so what we're doing here is if y is less than 5, meaning we're just set an arbitrary point for the ground, basically. If it's less than 5 tiles from the top, then just make it the sky. And so sky, we've just up here on line 24, 25, we just set 2 tile IDs, as I said before. Sky is 2, so it's going to be on the right side of the sheet, and then ground is 1. It's going to be the very first quad generated in the sheet. So if y is less than 5, that ID should be equal to sky, else it should be equal to ground. And so down here is where that comes into play. We're going to clear the screen with our color, our random color. We're going to iterate over the loop, as James said. We're going to get the tile at yx, tiles yx, and then we're just going to draw the sheet and the quads at that tile's ID. And then recall, since tables are 1 indexed but coordinates are 0 indexed, we take the x and the y, we subtract 1 from them, and then we just multiply them by tile size. And that has the effect of drawing each of those tiles at their respective point in the world and making it seem as if we have sort of this world, this bunch of bricks with a random background every time, which isn't all that interesting, but just a little bit more variety. And so that's the very basic gist behind. I mean, it's essentially almost the same thing as what we did in match 3, where we just mapped the individual tiles that were in the grid to indexes in the tile sheet based on the color and variety. Only this time, they're always going to be in the exact same place, so we don't have to worry about whether their x and y are different from their grid y and grid x. We're not maintaining a reference to those. And so that's static tiles. So does anybody have any questions about how we just draw static tiles to the screen? Pretty basic stuff. The sort of the namesake, or the sort of the whole name behind side-scrolling game is that the tiles sort of scroll based on what we're doing in the game. It can be an auto-scroller, in which case maybe you're like an airplane that's just sort of going through a level that's scrolling automatically, and you're shooting things, and you're not really in control of where you go. Or it can be like Mario, where you control an avatar, and you can walk around and jump and stuff, and the camera will always be fixed on you. And so the scrolling is just relative to where your characters X and Y are. So I'm going to show you guys an example of how we can get scrolling implemented in our game. And to do that, the function that we're really going to be looking at, a new function, is love.graphics.translate x, y. And so what that does is effectively just translates LÖVE2D's coordinate system so that whenever we draw something, it gets automatically shifted by x, y. And so that has the effect of the camera sort of, or everything being sort of drawn, skewed based on the x, y that we pass it. And so if we maintain a reference to where the character is, we can just shift where everything gets drawn on the screen, and that'll have the effect of it being a camera but it's not. All we're doing is just shifting the coordinate system based on some offset. X being, in this case, where the player is effectively.
So it changes the whole coordinate system?
It does. It shifts everything in the coordinate system that you draw by the X and the Y. And so that will basically affect what's getting rendered into the active window at that time. So I'm going to go ahead and pull up tiles 1 here so we can see how this works. Go ahead and first run the program. So if we're going into tiles 1 in the distro, currently it looks almost identical, but I can move it if I just press left or right. And so we can see here, this is where the 2D array of tiles gets cut off here. And then it also cuts off, because we're only generating a 20 by 20 level, it also gets cut off at the very right side as well. And these are details you would normally hide from the user by just clamping the X between 0 and sort of the right side of the map minus virtual height, or virtual width, sorry. And that will have the effect of whenever you get to this point, just it won't let you go right anymore, and same thing for the left side. Well, all we're doing right now, we're not doing it based on the character at all. We're just using mouse or keyboard input. So let's go ahead into tiles 1. And so the important thing that we're going to look at is, as I just alluded to, we're calling LÖVE.graphics.translate on some value called camera scroll. And it has to be negative value, because if we want the, it has to be a negative value, because if we're moving to the right up here or to the left, if we're moving to the left, camera scroll basically is going to decrement. So it's going to get less. So we can say the camera scroll when we're going left is going to be 0 or less if we're starting at 0, or it's going to decrement. If we press right, camera scroll should increase. If we want the appearance of moving to the right or moving to the left, you actually have to translate by the opposite direction. Because if everything's getting translated, if we look at this, and if we call LÖVE.graphics.translate positive, all of this is going to get moved to the right, so it's going to have the appearance of us moving left. And if we translate it to the left by a negative amount, it's going to have the appearance of us moving right. So we have to, if our scroll is positive and we want to move to the right, we actually have to translate by a negative amount. And so that's why I'm calling negative math.floor camera scroll. Does anybody know why we're calling math.floor on camera scroll instead of just calling math.scroll or camera scroll negative camera scroll? Does anybody remember what math.floor does? So math.floor will return the, it'll basically truncate the number down to the lowest number, integer. It'll basically take off the floating point value. Because we're rendering to a virtual resolution with push, and we have fractional, if we basically offset the translation by a fractional amount, you'll get artifacting, because it's taking your window and just condensing your image onto a virtual canvas. You'll get like weird blur and stuff like that. So whenever you draw something, basically, and you have a fractional number for something, and you're drawing it to a virtual canvas that's been magnified or it's being condensed, just make sure to math.floor it so you don't get any weird blur artifacting. You can, if you take this out and experiment around, or even if in the distro you take it out of the player's position, you'll see the player will get like weird blurry artifacty and stuff like that. So that's why that's there, in case you're curious. And so yeah, all we're doing here, we're just saying if it's equal to left, scroll the camera left, scroll it right, or basically give us the decrement our camera scroll and then increment our camera scroll, and then just use the negative version of that here. You could also just assign camera scroll equal to positive when you move left and negative when you move right, and then you could give it the regular camera scroll here, but it's sort of like mentally flipped in terms of this part, so I just made the decision to decrement it here when we're pressing left, because we're going left, and or going less on the X and then more on the X when we press right. Does this make sense? Anybody have questions?
I have a question. Is there like a corresponding function in JavaScript and in other languages like this where you can shift the whole coordinate?
Is there an equivalent function in JavaScript where you can shift the whole coordinate system? Not in base JavaScript, probably. I mean, I'm not too familiar with CSS. There might be a CSS function that does it. In a lot of engines, 2D game engines, yes, I would say. And a lot of actual 2D game engines will have a camera object, which sort of encapsulates this behavior. LÖVE2D doesn't have a camera. So this is sort of why we're doing this, is because it's kind of a lower level game framework, LÖVE2D. It doesn't really give you as many things right out the gate, which makes it great for teaching these concepts. But like a more robust solution, like Unity or Phaser or a lot of other game frameworks, is that they'll just have a camera object, and you just basically give that your X, and then you just move that you basically tell that to track the player, like camera.track track player or track entity player, and that'll have the same effect. It's a little bit more abstract. It's a higher level than what we're doing, but it's the same exact sort of principle underlying. So any other questions as to how this works? All right. Cool. So that's all we're effectively doing. We're just getting a camera scroll, decrementing it, incrementing it, and then just every frame, we're translating everything before we draw everything. You have to do the translation before you draw, because everything that you draw after the translation gets affected by the new coordinate system change. So that's scrolling. Let's get to actually talking about drawing a person, an avatar, more than just a set of tiles, since that's what the game sort of revolves around. If we look at character 0, this would be our first example here. This is just going to be a very simple example, character 0. You guys probably know how this works already. All we're doing is just drawing a sprite to the screen. So just love.graphics.draw. We're getting quads from a tile sheet, so the actual, I believe it's in the slides, the actual sheet is here. So we have this little guy, several frames of animation. It's 16 wide, 20 tall, and we just take a quad. We split it up into quads first, so we know that it's 16 wide by 20 tall, so we just generate quads on this image by 16 and 20. And then in this example, all we're doing is taking the first frame, which is quads 1, and just drawing that. As you can see here, we have a bunch of different things. We have like a crouching state, and we'll get to more about animations in a little bit. But here we have like him climbing up a ladder. But you can see all these different frames. We'll end up showing how you can like sort of play them back to back and get different animations. But for the sake of this basic example, all we're doing is just rendering the very first frame. And we can see that, make sure I'm in the right file, which I am. We are getting the character sheet here on line 43 and 44. And then we have to give him an X, so character X, character Y. In this case, we're just setting him above tile 7. So we do 7 minus 1 times tile size, because tiles are 1 indexed, but coordinates are 0 indexed. And then we just subtract the height so that he's right above the tile instead of right at the tile. And then down here, we do a love.graphics.draw on, as I said before, just character quads 1, just a very basic, hard-coded example. Any questions at all as to how this works? All right. So now, let's say we want him to move. What do we need? What's the next step if we just wanted him to move? Yes, give him an X and Y. So yes, so he does have an X and Y already. So if we look at, am I in the right one? So if we go to character 0, this is character 0 still. We have given him an X and Y already, but there needs to be another step. What's the other step involved? So if we want him to move, we need to check for keyboard input, and then we need to sort of take his X. We're just going to move him on the X-axis for now. But we basically need to take his X, his character X variable up here, and we just need to modify that. We can basically do the same thing that we did down here in love.update on the, previously it was on the coordinate system, love.graphics.translate. We modified the camera scroll. We set that equal to like scroll speed times delta time. We subtracted or added it. In this case, what we're doing is we have a new constant called character move speed, and we're just doing that exact same operation, but on character x instead of camera scroll. So the end result of that is that we have the character here, and then we can move him left to right. And he can go off screen. Now there's a couple things wrong. What's wrong? What are some of the things that are wrong with this scene right now?
The camera should move with him.
Camera should move with him. Does not have animation. Those are probably the two real things that are wrong. So doesn't move, camera does not track him, which is an important thing. Obviously, we want to be able to maintain a reference to our character unless we're at the left edge of the screen. If we're at the left edge of the screen, this is actually OK. And that's part of the distro, is we clamp the X so that it doesn't go past the left edge. But if we're beyond the middle, and not to the right edge of the screen, it should be moving along with him, and vice versa. And then he needs to animate. So his sprite needs to change every sort of number of seconds, whether he's moving. And it has to be only when he's moving, right? Like if he's standing still, I mean, you can have an idle animation. Like some characters will kind of tap their foot and do stuff like that. But let's say for the sake of this sort of example, we want him just to stand still when he's idle, and we want him to have an actual animation when he's moving. We need to take care of these two pieces. 3 pieces if you count the idle animation part. So let's go into character 2 and take care of the first part, which is tracking him. So I'm going to go into character 2. Let's run it first so we can see what it looks like. So now the camera is basically affixed to the player. In this example, we don't take care of the left edge issue. In the distro, that's fixed. But we have the basic, side-scrolling mechanic. Take a character, follow him. And how do you think that we're accomplishing this? Yes?
Translate the drawing against the character X?
Yes, exactly. And it can't be exactly the character X, though, because if it is, then the character is going to be on the left edge, right? So we need to offset our X that we translate by. We need to basically translate by his X minus half the screen space plus half the character width. And that'll have the effect of translating it, but always keeping that offset half a screen width away from the player, if that makes sense. And so what we're doing is in character, I believe this is character 2, right? Character 2. We're still doing the same thing we did, but actually that's the wrong file. We are modifying character X here. So, same thing we did before. Multiply the move speed by delta time and either add or subtract it if we're pressing left or right. But also here, we're reintroducing camera scroll. And we're setting it to, like I said, character X minus virtual width divided by 2, half the screen, and then positive offset of his width divided by 2. And so that he's perfectly right in the center. Because remember, characters their coordinates are set by their left, not their center. And then we just do what we did before. We translate the scene based on camera scroll, and then we render him at character X, character Y, using math.floor to prevent him from being at a fractional point in our world space and then being blurry and artifacted. And that's sort of it in terms of how we can get tracking of our character. And if you wanted to track along the y-axis, you could do the exact same thing. Maintain a camera scroll X and a camera scroll Y, so keep them separated. And then you would just translate here. You would just pass in. So we're passing in 0 because we don't want to track along the y-axis necessarily. But all you would need to do is then pass in your Y camera scroll, and then you could do it, based on character Y and whether or not they're above the ground or past a certain point in the sky. So any questions at all as to how the camera tracking is sort of working here? All right. So we took care of one issue, which was the sort of lack of tracking. But there was one other issue, which was he's not animated. All he's doing is just sort of walking on the, he's just moving, sort of doing like the MC Hammer, or is it MC Usher? MC Hammer? I forget. He's doing that. He's not doing anything. We need to actually animate him so that he looks like he has some life to him, and that you can also differentiate, importantly, between 2 separate states. He can be idle, he's not moving, and he can be moving. So he should be we should have some sort of visual feedback as to what's currently going on. So anybody know how we can go about implementing sort of an animation for our character? What are the pieces that we'll need?
I guess if he's moving right, then call a function in render that kind of loops through some images?
Yes, so if he's moving right, then loop through, or have a function that sort of loops through some images. That is effectively what we will be doing. We have a class called animation, which I've introduced here. And all it basically does is keep track of, you pass it in a table, which has the frames of the sheet that you want to animate over. So we can just pass in, let's go ahead and take a look here. We could pass in, and I referenced this slide earlier, but all of these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, however many there are. You could have, you just pass into the animation, maybe you want, let's say he's on a ladder. So let's say this is, what is this, 1, 2, 3, 4, 5, 6, and 7. You say the frames are going to be 6 and 7. So those will just loop sort of left to right, starting back at the beginning when it's finished. And then you give it an interval. So say I want the animation to happen this fast in terms of seconds. So I want it to maybe happen every 0.2 seconds. And so that'll have the effect of every 0.2 seconds. It'll keep track of a timer. So have we gone over 0.2 seconds? Start at 0 and then add delta time to it every time. If we have, increment sort of like what our current frame of animation is. So our current frame is this one. And then 0.2 seconds elapses. It's going to be this one. And then 0.2 seconds elapses. Then we need to loop back to the beginning. So we'll end up using modulus to take care of that, as we can see in the animation class. Basically, that's all done here. So if we have more than one frame of animation, so recall, it gets a def here. So we get frames, we get an interval, get a timer that's initialized to 0, and then get a current frame. We'll say the current frame is 1. And then as long as we have more than one frame, there's no point in looping over, trying to animate any animation that only has one frame. And we can, of course, have animations that only have one frame. Idle is only one frame of animation, as we saw here. Like, that's only one frame. We don't need to do any sort of logic to say, oh, what's the next frame? Because there's only one frame. But if we were to look at character 3, we can see 2 frames there. And then that's just one frame. He's idle. And when we move left, he moves in that direction. Anybody recall how we can get him? Because obviously we saw the sprite sheet just a second ago, and there was only one direction that the sprites were facing. How we can get him to sort of look that way, even though there's no sprites for him to look that way?
Flip it on that axis.
Flip it. So LÖVE.graphics.draw. Recall you can pass in a negative scale factor on whatever axis you want, and that'll have the result of flipping it along that axis. So that's all we're doing. So this is the default frame, so we're just drawing it, and then we have to keep a reference to whatever direction he's facing. And if his direction is equal to right, we'll just draw that frame and then loop or process the animation. If he's facing left, draw it, but also perform a negative x-axis, -1 transformation on the x-axis. And just like that, we sort of have that working. So all we're doing, just keep a timer, and then when the timer goes over our interval, sort of just increment the frame, and then use modulus to loop back over it, back to starting at 1. And that's all done here on this line 28. And so you can look into there a little more if you want to get a handle on sort of how the math works. But it is just a simple sequence of iterating over a collection of frames based on a timer. And that has the effect, just like a flipbook, as I said earlier, of our character having an animation, having some life. So any questions as to how animations, or this animation class works?
The render is in the animate class?
So no, the render is not in the animate class. So the render is, I realized I didn't show it in the actual main here. Well, we have 2 animations here, which was just the idle one. So we're just passing in 1 frame. We're still going to give it an interval of 1. It's not going to really matter, but just for the sake of consistency, we're going to give an interval of 1, arbitrary. And we want to change his animation later. So by having an interval here, we won't forget to add one later. Moving animation, recall 10 and 11. So it's toward the end of the sheet. We're to 2 walking frames. Interval here is 0.2 seconds. We need a current animation to render him. And then we keep a reference to whatever direction he's looking at. So if he's looking to the right, we're going to reference this in the LÖVE.graphics.draw at the bottom. and that's what we're going to use to perform the sort of sprite flipping along the x-axis. Maintain a reference to that. And then down here, the part that we actually reference the animation is on line 150 if you're looking at character 1. Or is it character 2? Character 3. If you're looking at line 150 in character 3, we're using current animation get current frame. So the class will actually just tell you whatever the current frame of animation is, because it keeps a reference to what frame it is, and, based on the timer and like how much has elapsed.
So the class is generating a different frame real time.
Yep. Yeah, it's maintaining a reference to whatever the current frame is, and it's in the table of frames that it got when you gave it the definition up at the top here. Lines 51 to 58, where we create the two animations. Basically, it maintains a reference to which index in this frame table we're at. So if 0.2 seconds has elapsed, we start at 1, and then we go to 2, and then we'll go back to 1. And so it'll just basically return frames index. And frames index 1 is 10, frames index 2 is 11. And so the function is get current frame. So character quads, current animation, get current frame. And then here we shift because we're performing an origin transformation. So it's another thing to consider when you're sort of flipping sprites. When you flip a sprite, it actually flips along whatever its default origin is. And the default origin of any sprite is its top left corner here. So if you flip something along its x-axis, it'll appear here instead of just flipping in place. So you actually have to set the origin to its center when you do any sort of in-place flipping of a sprite. So you'll notice in the code when you're looking at it that we have plus character width divided by 2 and plus character height divided by 2 on these two here. So we shift where it gets drawn, and then we shift its origin offsets, which are here on line 160. So if you look at love.graphics.draw, you'll see it has a lot of optional arguments. And these two at the bottom are the sort of origin offset arguments. And so these only really come into play when you do some kind of flipping of a sprite on an axis, and you want graphical sort of consistency, not to have it flip one way or the other. Sometimes that's the effect you're looking for. But in this case, it's not. We want him to literally stay in the exact same place. So to flip a sprite in the exact same place, you need to set its origin to its center, not its top left. Does that make sense? OK. And also here, this is 0 is the rotation here. So it's sort of required if you're going to add this many sort of arguments to the function. But we're testing if direction is equal to left, we want to flip by -1 on the x. Else just give it 1. So 1 just means default transformation, so no flipping. And then we don't flip on the y at all, so that'll always be 1. And so that's sort of in a nutshell how you can get your character to animate and also stay in place when you animate it. So any questions as to sort of how animations or the origin offsets or any of that work? OK, so we did talk about animations. The last thing we'll talk about for the character is jumping. So if we recall from Flappy Bird, how can we get our character to jump? What are some of the pieces we need?
Key press and then get the Y. Y goes up and then you have some gravity.
Yep. So key press, one thing we need. So we're check for space is going to be the default key. Y goes up, and then check for gravity. So we need, not only do we need y, but we also need delta y. We need velocity, because gravity is a transformation on velocity, not strictly on position. So if we go back to character 4, this is sort of a hackish way of implementing gravity, because we haven't actually incorporated tile collisions, and I'll defer most of the sort of implementation for that is to the distro, and I'll sort of go over it with you guys. But right now we have the exact same thing we had before, where we have tile scrolling. But if I press spacebar, I go up, and then he comes down. And notice that he has an animation as well. He has a different frame. So if he's jumping, he's got a little jump frame. So that means now we have 3 animations. We have an idle animation, we have a moving animation, and then we have a jump animation. So effectively, we have 3 states as well: idle state, moving state, and jumping state. Oh, 4 states, actually. And there's also, I noticed a slight bug here where if you're still in the air, his frame doesn't change. So it actually probably should stay to that frame even if he's standing still. But I guess it doesn't matter too much. It could be also interpreted as a feature. But he has got a couple of important, a couple of states when he's in the air. There should be 2 states here. One is jumping state and one is falling state. And do we know why the 2 being different is an important thing? So if we think about Super Mario Brothers, and we think about the sort of differences between jumping and falling, what are some of the things that change based on whether Mario is jumping or whether he's falling? How does he interact differently with his state, with the environment, I should say? So if familiar or if unfamiliar, Mario, when he jumps, he can actually hit blocks. So if he's below a block and he hits a block that has some sort of behavior in it, it'll trigger whatever is in that block, whether it's a coin or whether it's to destroy the block. And if he's falling, recall, if he lands on top of an enemy, like a Goomba, he'll destroy the enemy. And so we sort of need to distinguish between these 2 states, because when he's jumping, he's not able to, like when he's actually going up, he can't attack the enemy. And likewise, when he's falling down, he can't destroy the block. So even though he's jumping up in the air, and the sort of gravity is applying a transformation, and it sort of all looks like one state, there's actually 2 important states, 2 important changes in his state that are relevant. And that's something that we'll need to pay attention to, and it's in the distro. He has a falling state and a jumping state. Even though they share the same animation, they have different behavior. So let's go ahead and look at the character 4 distro here. So what I've done here is I've added a delta y for the character. So just like in Flappy Bird, when we press space and we made our delta y go up to like -50, so instantly like shot up pretty high because I was getting applied every frame. Same thing here. Once we press space, we're going to change delta y to -50. If we go down to, where is it at? So right here. So if the key is equal to space, I have it in the LÖVE2D function. Since we're doing all of this in main.lua just for illustration, things are a little just sort of simple. If key is equal to space and his delta y is equal to 0, what would happen if we didn't check to see if delta y was equal to 0? Yep, we'd be able to jump infinitely. So we have to do a check for that. We set his dy to jump velocity. Jump velocity is a constant up top on line somewhere up here. 29, which is just -200. And then gravity is equal to 7. And so what we do is we set it to -200, his delta y, as soon as he jumps. And then every frame, down in update, we basically increment his delta y by gravity, and then we increment his y by delta y times delta time. And so I have the effect of it when he's in the air and he's got a negative velocity, it'll actually start becoming positive and positive until it is positive, and then he falls back to the ground. And then the hack that I was referring to earlier, since we don't have collision detection implemented in this example yet, is we're just basically checking to see whether he's gone below the map's floor, what we set the map's floor. And if he has, then set his position, first of all, to be above that tile here on line 133, and then set his delta y equal to 0. And that'll allow us then to hit space again, because his delta y will be equal to 0.
So, I didn't see if statement around it. It looks like there's always gravity.
There is always gravity. Something I realized like shortly before lecture, but all you would really have to do is, I think, if character dy, yeah, you could easily take that out of there, just an if statement around it.
It's just wasted resources, right?
It is. I mean, it's not expensive, because all you're doing is incrementing a variable by a certain amount. But it's, I mean, because if anything, if you're introducing an if condition every frame, which is probably the same, if not actually more, I think a branch is more CPU than just an assignment. I'm not entirely sure about that, but yeah. Yeah. In this case, it doesn't really have any side effects, but it's a good thing to notice. But now notice that we can just sort of walk along the floor here because there's no collision detection. We'll talk about how we implemented collision detection soon. So one thing that we'll start talking on, and we'll take a break fairly soon, is procedural level generation. So I am a big fan of procedural level generation, and platformer levels are actually fairly easy, at least in a simple sense, to procedurally generate. And so, like with match 3, all we basically did was just loop through our grid and just say, oh, get a random color and a random variety, and then with the assignment, it was a little bit more complicated where you actually had to check to see whether you were on level 1, and then if you weren't, then your variety should be, maybe a certain amount depending on how far along you progressed in the game. With a procedural level, or with a platformer level, sorry, we sort of have to think about how we can take that basically grid of IDs, of tile IDs, and sort of think about it mathematically. How can we sort of get the results of a level, but make it different every time, like introduce some variation, right? And so the solution that I found that makes the most sense is going sort of column by column. So here, if we just have a bunch of, this is just a very simple, perfect screenshot to illustrate a very simple way of generating the level. But recall, if we just think about these tile IDs, of these tiles here, this empty space as being like a 0, and these being like a 1, so sort of almost like binary in this case. We could just fill the entire thing with 0 first, just assume empty space, and then we could just row by or column by column just go down and just have a chance every column. Okay, do I want to generate a ground here? If I do, start at like the ground level and then just generate earth tiles all the way down. And then go to the next X position, do the same thing, and then maybe every column of the world that you're generating, you also have a chance to generate a pillar, like this. So if like generate pillar is true, then I want to spawn, instead of starting the ground here, I want to start it here. And then maybe you have a flag that says, okay, not only do I want to generate pillars, I also want to generate just chasms, just empty space, obstacles for the player. Right? Because if he falls down, it goes below the world space, it should be game over. So in that case, you just say if like generate chasm, like math.random 10 or whatever it is, then just like go to the next X, like don't even do anything. And that'll have the result of generating a chasm. And so a little piece by piece, doing small things like that has the net effect of generating a lot of sort of visually interesting dynamic and random levels. You never know what to expect. And this is a very basic example. You could go infinitely far with it, however many ideas you have in terms of sort of how to create obstacles and interesting levels and scenery for the player. Like you could absolutely implement that.
How do you handle if there's like a platform to jump on? Because you have to have that consistency.
Yeah. So if it's a platform, so it depends on how you want to implement platforms. If it was let's say if you wanted to implement, and this is actually, I did a seminar on Super Mario Brothers, and we did platforms as like tiles. In this case, we'll have blocks that are actually what we've denoted as game objects, which are a little bit different than tiles because they can have arbitrary sizes and they don't necessarily have to be affixed to the world grid. But if you were to treat these tiles as, or if you were to treat a platform that was like, let's say, 2 tiles wide, as tiles, all you would do is just basically have a flag like up here that's like generate platform equals true or whatever.
And then turn it off after.
Turn it off after however many iterations. You also need the size of it. You'll need a flag that's like platform width equals however many. And so you'll just keep a counter. It's like a current platform tile equals 1, 2, 3, and if it's equal to width, then you don't generate it anymore. And that has the effect of potentially colliding with pillars if you don't account for that. So you can also, in your logic, say, if I'm generating a platform right now, like don't generate a pillar. But you could generate a chasm because the chasm doesn't interfere with your platform. And then you can also just, if you don't have things as, if you don't have platforms as tiles, if they're different objects, then you can just, you don't have to do it during the actual world generation phase. You can just you can just create a game object that's a platform at a certain, depending on how complicated your algorithm is, maybe make sure that it's not next to a pillar when you generate it. And you could just do that by getting like the tile here and then looking at the next 4 tiles, something like that. We don't do platforms in this example, but it's something that you could pretty easily do with tiles, and slightly more difficult, but it's also still fairly easy to do with game objects, which is included in the distro, and which we'll touch on in a little bit. Let's see, we're at level. Oh, a couple of things that I wanted to show before we actually start getting into the code for how to generate levels is this is the sprite sheet for this whole project, which is a really cool sprite sheet that I found online. It's in the spirit of platformers like Mario, and it's got a nice little mock-up here on the right. So I encourage you to take a look at that and just maybe get some inspiration and see all the different cool stuff. Tinker around with it if you want to. But as you can see here, there's a couple of pretty prominent things. We have a ton of tiles. These are all tiles here, different tiles and variations. And then we have a ton of these toppers here. And so what really, I think, helps this whole sort of demonstration of generating these levels is the fact that we have so much visual content to work with. And so here, again, are the tiles. Here are the toppers. And then when you sort of take the two together, and then you also have these random backgrounds, like these are toppers here, like the little top of the tiles here. It's incredibly easy to just have a sheer abundance of visual variety and interesting things in your game levels without even, and the algorithms here are very simple. All we're doing is just checking to generate pillars and columns. I don't know. I thought it was really cool, and it sort of helps illustrate the sort of importance and power of this whole procedural approach to creating the levels for this. And there's actually not that many games that take advantage, I think, of procedural level generation in the platformer genre. Plenty of games like Minecraft and Terraria. I mean, Terraria is a great platformer that is an example of that, but I don't think I've seen a really good Super Mario Brothers game that does something like that. But let's see, what time is it? 6:23. Why don't we take let's take a 5-minute, and then as soon as we get back from that, we'll start going into how we actually can implement this sort of procedural level generation in more detail. All right, welcome back. This is lecture 4, and before we took a break, we were talking about procedural level generation in the context of platformer levels. So recall, here are just a few examples that I took pretty quickly of sort of my code. And you can see they have different backgrounds, different tiles, sometimes we have chasms, sometimes we have pillars. We'll be talking about a few ways to do the tile version of sort of that, because there's 2 levels here. In the distro, we'll see there are also things like bushes, for example. We can see in the top middle there the purple I guess those are little like purple cacti. And then like the one right below that, there's a pillar with a yellow sort of fern on it. Those are separate objects from the tiles, game objects. But the actual tiles themselves, we'll sort of dig in here a little bit as to how to get those generated. So the first thing we want to look at, level 0, is just some flat levels. So just basically what we've already done. So I'm going to go ahead and go into, oops, not lev 0, level 0. And then if we see here, we have a simple flat level just like we did before. Now the tiles are different, and if I press R, they're randomly generating every time. So we can sort of get a sense of just how visually diverse this sort of generation looks. I mean, we're not even, I think that might have been a bug earlier, I'm not sure. Haven't seen that yet. But we can see here, I'm pressing R. All I'm doing is taking basically the array of tiles that we have, and I'm assigning it a tile set and a topper set in the case of sort of this, the scope of this generation. So recall that the topper is just the top layer sprite, and the tile set is just the sort of the tiles underneath. Anybody know, sort of like, want to just suggest how I'm sort of rendering the topper versus the tiles and what's going on there?
Just pointing from the part of
Yes, I mean, yeah, in a nutshell, I'm just pulling the toppers from a different part of the sheet. Any idea how I'm storing the information? Like what's being stored here to get it to render like this?
Maybe you just need to store the position of the topper. You know that everything else goes below that.
Yes, so you could store the position of the topper and know that everything else is below that. That would work for a flat level. It would be a little bit, I don't think that would be reliable for a level that has pillars on it, because the pillars are a higher elevation than the ground, and then there's also chasms and stuff like that. So what's going on here actually is we're storing basically a flag in a tile that says whether or not it has a topper on it. And if it has a topper, then we render not only the tile, but as soon as we render the tile, we also render the topper. And I won't go too deep into the code here, but what we're doing to get all these different tile sets and topper sets too is we have to take all of these basically tile sets, these collections of tiles, and sort of divide them up, right? We have to know that if we want to render the entire level in tile set 1, then we should, have basically take this into its own sheet, its own table, this into its own table, this into its own table, going left to right actually. And we have basically a sort of like a four-way nested loop. So we go, every set on the x by every set on the y, and then within each of those, we want to look for every tile along the x and every tile along the y therein, and split up the tile set so that we can index into the individual quads. So in the actual code, I won't go too deeply into it here, but I'll show you where it is if you're curious to look into how we do that. It's in Mario, in source, util.lua, which is, recall, where we before stored our generate quads function, which does a simple split on a tile sheet along its, just along x and y based on whatever width and height you pass in. We have in here also a generate tile sets function, which takes in the quads from a generate quads table. So we first generate quads on all of this or all of this. So we have every single frame of this divided by 16, which is, I don't know how many that is, 6 by 5 times 1, 2, 3, 4, 5, 10 by 5, 10 by 4. That many quads, so like thousands of quads, I think, if not hundreds. This I'm pretty sure is thousands of quads. And then we take that and then divide it into using the number of sets along the x-axis, sets on the y-axis, and then the size of each tile set along the x and size along the y. We do a four-way, basically divide it using a four-way nested loop here. Basically just divide it up and then do instead of doing a generate quads along the entirety of the picture, we just do it along basically do a 2D slice of that quad table we get back from the first generate quads call. So I would encourage you to sort of look in here and experiment with that. You don't need to necessarily know how it works for the assignment, but that's how we can basically take a giant sheet like this and easily just sort of integrate it into our code. We can just swap in and out whatever active tile sheet we want to work with, assuming that everything is cleanly laid out like this, which is on part of you or your artist. You want to make sure that everything is conducive to programmatic sort of organization. Had things been scattered around in a very awkward way, maybe things were like zigzagged or like there were weird spaces or something like that, we wouldn't be able to do something as clean as what we did here in util.lua with just 63 minus like 20 lines of code by getting each individual tile set. So that's an important consideration if you're looking at creating assets for your project and you want to do some programmatic hot swapping of your tile sets. Let's make sure we're not in the right example here. So we're going to go into level 0, into main. And we keep track of, we have constants now for all of our tile sets and what the height is and how many they are wide by tall. And we effectively do, we do it here. We get our regular quads from our tiles and toppers. So these are just literally every single tile within that big tile sheet put in one table. And then we just divide it up into tile sets and topper sets here with the generate tile sets function. And then we get a random tile set and a random topper set here. Math.random, number of tile sets, number of topper sets. And then at the very bottom, also we have a generate level function, 223, which is going to be built upon in the next two examples. Level 0, just flat levels. So it's actually exactly what we saw before, which was just if ID is less than, if y is less than 7, ID should be equal to sky or ground. And then this part is actually what I was alluding to before with the topper. Because recall, we need to store a flag in a tile to render a topper or not. And it should be whatever the top tile is in the level on the ground. In this very simple sort of flat thing, we can always assume it'll be the same y level. In this case, if it's equal to 7, then topper should be true, otherwise false. So every tile along y7 is going to have topper equals true. And this comes into play up here. If we do love.graphics.draw tile sheet, we have not only just tile.id as we did before, but we have tile sets indexed into tile set now. So remember, tile set got a random value between 1 and however many tile sets we had that we sort of spliced out of our massive tile sheet. Now we just index into that, and then we index into tile.id. And tile.id will then be whatever our ID is, but relative to that sheet, not the whole entire sprite at once. And the same thing for topper. We have a topper set. We index into topper sets here at the topper set that we got, and then that's where we'll have the collection of tiles that form that particular set. And so the two are completely separate. They can be one random color tile with one random topper, but it's consistent. It's global. We have one topper set, one tile set that are active at any one time. And if we press R, which I did up here, then we just reset them to random on line 139 and 140. Tile set gets a new random number. Topper set gets a new random number. Has the effect of we can just walk around and then just generate random sets. So pretty simple, and recall again, topper is on because the tile that we're standing on is y7. Topper equals true, so in that case, that particular top layer is always going to have a topper. And it gives us a nice little bit of visual variety because it actually makes quite a bit of a difference having a topper versus no topper. And you could also just not have a topper and consider that a permutation of the toppers times tiles, like procedural algorithm. But that's flat levels. Does anybody have any questions as to like sort of how this works or anything that we're doing here? OK. So things are a little flat, a little boring. The next step will be actually introducing one of the things that we can see here in our little collection of sample levels, like this pillar right here in the very middle. Does anybody recall how we go about spawning a pillar as opposed to just flat land?
Just for that column, just put some more dirt down or more tiles down.
Yep. So for that column, just put more tiles down instead of just the ground level. It's exactly what we're going to do. So I'm going to go ahead and open up level 1 in main, and I'll run the example here as well, just so we can see what it looks like. Whoops. So here we have quite a few, and notice we haven't implemented collision, so we're still walking through them. But we have, they're just random. The random amount is up to taste, really. Right here, it's pretty common, so it might be worth lowering the amount a little bit. If you wanted to, you could also maybe have a flag that says spawn pillar, and maybe you want a pillar width. You could have, anywhere between 1 and 3 tiles, and if its width is, greater than 1, then just, like loop over a few times and just like draw that same height a few times as opposed to just one time, and then set the flag back to false. A lot of things you could do with it, and also they're a little tall here. For the main distro, I ended up making them a little shorter. But we'll see how we do this in the code here. It's going to mostly be down in our generate level function. So what we're doing here, go ahead and hide that, is we have basically this code here, line 227 to 236. So all we're doing here is just filling our entire thing with just sky. We're just setting the entire thing to empty. And now we have a fully populated 2D array. All we need to do in order to change a tile, we don't have to worry about insertions or adding too many tiles to our array. All we can do now is just directly change whatever tile exists there. So all we need to do is, starting on line 239, we're going to start doing the column by column iteration over our entire level and deciding whether we should generate pillars or not. And we're always going to generate ground. So here's the flag, spawn pillar. And if it's equal to 1, it's going to basically be assigned to spawn pillar. So math.random5 is equal to 1. We have a 1 in 5 chance of spawning a pillar. If we do spawn a pillar, then just pillar gets equal to 4 from 4 to 6. So from tile y, for y gets 4 to 6 effectively. Tiles at pillar, x, ID ground, and then here's where we set the topper, recall, because now pillars can be the topmost tile basically on the surface, but they're above the ground level. So we just basically say, when we're generating a pillar, if pillar is equal to 4, which is the very first tile that we start at, then set topper equal to true here. Otherwise, set it to false. So that's how we can get pillars to also have toppers. And then always generate. In this case, we're not generating any chasms yet. So all we're going to do, once we've generated pillars, once we've generated a pillar on that particular column, we'll just say ground gets 7 until the map height, so towards the very bottom of the screen. And then we'll just set it to ground. And then topper, in this case, we're going to make sure that we're not spawning a pillar, because if we don't check this, then it'll also spawn a topper like where the pillar meets the ground, and it'll look a little bit silly. And then we also want to check that ground is equal to 7. And so altogether, that has the effect of sort of this behavior. And so if we didn't check for that not spawn pillar, we'd have like a topper right below our feet here too, which looks graphically strange. But that's how you, and also you can see like emergently, we're getting like double-sided or double width pillars. And that's just kind of a natural byproduct of a lot of these randomizations, a lot of these sort of procedural algorithms. They'll generate outcomes that you might not necessarily have anticipated, which is kind of a cool thing. Like you didn't necessarily program it to have pillars that were 2 tiles wide, but just the nature of randomization, that's just sort of what you get. And that's another exciting thing about procedural level generation is like it can surprise even the person that wrote the algorithm. Like it's really cool. And it saves you work having to create levels. So that was pillared levels. Chasmed levels. Who can tell me how we can do chasm levels? Yep. You skip a column. So at the very beginning, all we can just basically say is, do I want to generate a chasm here? If I do, just skip. Go to the next iteration of the loop. And so we'll take a look at that. Even as simple as it is, because Lua doesn't have the notion of continue, this will be a refresher because I believe this was in one of the assignments. It has a go-to statement. So basically, same code as before, starting at column by column, x equals 1 until map width. If we have a 1 in 7 chance, just arbitrary. And this should ideally, if you're engineering an entire large game or application, this would be called like spawn chasm chance probably, and just set that to 7 somewhere. But we're just setting it to 7 here, just a static magic number. But magic numbers are generally bad. Go to continue. And so continue is here at the very bottom of the sort of the loop here, which is this for x equals 1 map width. So it'll have the effect of skipping straight to x equals 2 if this is at 1, for example. A lot of languages just simply have continue. Lua does not have continue. So this is a community established sort of tradition for implementing continue-like behavior in Lua. You create a label via double colon with a name and then a double colon, and then you just go to it. And so that's as simple as it is for generating chasms. And so if we go back to, if we go to level 2 and run that, we get chasms. And so now we've got sort of like a little bit of interesting visual variety. It's not spawning a ton of chasms in this example. It spawned 1 so far. There's another one. And then sometimes, just emergently, you can get 2. Oh, and let's see, there we go. We get some interesting obstacles as a result. Like almost looks as if someone intentionally did that. Almost. I would probably, like I said, shrink the pillar size a little bit. It's a little tall, but that's that. That's basic procedural, like in the context of platformers, like that's how, like that's the mental model for how we can start thinking about generating, you know, obstacles. And there's a lot of different directions you could go. Let's say you maybe wanted to like generate pyramids of, I mean, there's a common thing in like Mario, like there'll be steps, and like CS50 has a P set for it. Like the same implementation would basically happen here. I mean, it would be a little bit different because you're doing it on a column by column basis, but you'd effectively just maintain a reference to something like step height. And then you would say like, generate stairs is true here. And then you would just set step height to 1. So then you add a tile here. You would go like from ground level up until step height, generate a tile. Go to the next one, and then increment step height to 2. And then do from, you know, ground until step height, tiles go up. So 1, and then 2, and then 3, until you've gone to stairs width, in which case you stop generating stairs. Like that's, you know, this sort of principle behind how you could do something like a little more complicated. Or pyramid, same exact thing, pyramid width, and then you just go until pyramid width equals, or we're at pyramid width divided by 2, you know, make it go up, and if we're higher than that, just make it go down, and then you have the effect of a sort of the pyramid approach. Yeah.
So where are you putting the column generation, and you know, if it's a pillar, if not, is it in the? It's not in play state. It's in.
In this case, it's all in main.lua, but in the distro, it's going to be in levelmaker.lua. So we've broken out all of this functionality into just sort of how we did, what was it, Breakout. We had the same sort of thing, level maker, and it just has levelmaker.generate, and then you give it a width and a height, and then it'll generate an entire level for you.
An entire level, but it has to continuously. Oh, you generate it all at once. It doesn't generate as you walk.
The question is, does it generate continuously or all at once? It just generates all at once. Oh. So you could implement if you wanted to do like an infinite runner, you could do the way you would do that is you would break up your level into chunks. And with infinite runners, usually you can only move in one direction. So as you go right, your levels that you've generated before, they get discarded, so you avoid like memory overconsumption. What you would do is you would just generate a chunk, like maybe a 100 by 20 level, and then you would like, you know, going through that, and then when you get to like level end minus maybe like 5 tiles or 10 tiles, you would generate another one, append it, like put it to the right, and then you would just like, you know, go from the left to the right. And you probably would need some sort of fancy, semi-fancy code to sort of like splice them together once you've generated them. Alternatively, you could just always pad your, oh no, I probably wouldn't want to pad. I would say, yeah, I'd probably just splice them end to end and then get rid of x equals 1 to 100 or however many on the left once it's gone past the left edge of the screen. But in this case, to summarize, yeah, just it's all static. But you could very easily, not easily, but you could very well make it an infinite runner. So, yeah.
So are we rendering like the entire level, but like we just can't see it all?
The question is, are we rendering the entire level, but we just can't see it all? The answer is yes. Currently, in this implementation, we're just rendering the entire level. So tile by tile is getting drawn to the screen. For small examples like this, it's not a concern. But for a large level, like if we did like a Terraria level, for example, Terraria is like thousands and thousands of tiles wide by like probably 1,000 or more tiles tall. You want to render only a chunk, only what you can visibly see. And for that, you could use your camera offset and then just like render one tile from one tile to the left and above that to one tile below the bottom edge of the camera and to the right of it, just render that subset of tiles. So you just need a loop, a for loop, to iterate over a small section.
So you can kind of make an array of what the map's going to look like, and then just render only slices of the array that you can see. Is that right? Like you put like I don't know, like a multi-dimensional array, and then you just go through it and render as you go. Is that the thought?
Question was, you just have a multi-dimensional array of tiles for your level, and then you just render it as you go. The answer is yes. You would have your overall tiles, your big 2D array of 100 by 20 or however many thousands of tiles. And then based on wherever your camera's rendering, you just draw it's just a for loop within that, just of a nested amount. So from like maybe your player is at like X player, like 30 plus 6 tiles. So you would just render from like 30 tiles to like maybe 45 tiles on X and maybe 10 to 20 on the Y, just that chunk, and it's just relative to where your camera is. You're always rendering like just a small little, basically it is effectively a camera at that point. You're just rendering a chunk of the tiles to the screen.
But in this code, it's not doing that.
In this code, no. And the levels here are, it's sufficiently complicated to introduce, and it's not too complicated to introduce, it's pretty easy, but the consumption, the sort of like the processing here is very light because the levels are fairly small, and even if we did have really large levels, it's sufficiently small to not have to worry about it. But if we did get to a point where your levels were 1,000 tiles or more, and then maybe those tiles have additional, like you just want to squeeze all the performance possible out of your application, you could look into just rendering a subset. It's fairly simple to introduce, but just not something that we included in this assignment. So, any other questions as to how this sort of thing works? Okay. So far, we've talked about procedural level generation. We've talked about sort of animation and rendering and all that stuff. We haven't really talked about how to do tile collision. And we won't go into a terrible amount of detail because the code is a little lengthy. It'll be part of your assignment to sort of read over it and understand it. But it's in the Tilemap class that we have. Basically, the whole gist is that because we're on a 2D tile array, basically, that's fixed. It'll always be at 0, 0, at least in the model that we've currently implemented. We can just convert coordinates to tiles and then just check to see whether or not the tiles at whatever that is are solid or not. So like we can check our character. Let's say we wanted to look at the sort of left, like the top of our character in this case. So if we have our character here, and let's say for the sake of illustration, I put him between 2 tiles above him just to show why we need to do this the way that we are doing it. But you take the point here, this very top left, so player.x and then player.y, which is effectively their version of 0, 0, and then player.x plus player.width minus, we do a -1 just to, for a lot of actually the sort of collision so that he can like walk between blocks and stuff like that. Because if you don't basically give him slightly less than the amount because he's 16 pixels wide and the tiles are 16 pixels wide, if he's between like 2 blocks and you want him to fall down, he just won't fall down because it's still detecting a collision because it's, even though it's, because if he's on the hole here, let's say this is the hole, this is the tiles here, the x plus the width, it'll trigger a collision on this tile and this tile still. So basically you need to minimize his collision box by 1 pixel to get him to fit through 16 pixel gaps, essentially is what it boils down to. But the gist behind collision, in this case, this would only apply when he's jumping because this is the only time at which he can really collide with tiles that are above him. You would test for whatever block falls on this pixel and whatever block falls on this pixel. And if either of them are solid, you trigger a collision. And if not, then there's no collision at all. So if he's like right here, for example, like right directly beneath a tile, it's only going to check 1 tile. This point and this point are both going to fall on this tile. But the reason that we want to check for both points here and here is in the event that he is beneath like 2 separate tiles. Because now this point's going to check this tile, and this one's going to check this tile. We can't just check this tile, because if we only check this tile, and there was no tile here, but there was a tile here, him jumping would still not trigger a collision, because it would think that it was only looking here and not here. So we need to check for every collision on every side we do of him effectively, we need to check his top. We need to check both corners of that edge effectively. So when he's jumping, we turn this point, this x, y, into a tile by just dividing it by tile size. So we can say player.x divided by tile size plus 1. That's going to equal whatever tile this is on the x, and then same thing for the y. We just divide the y by tile size, and then we add 1 to it. And that'll allow us to get the exact tile. If we use those x, y that we get from that operation, we get the exact tile at that y, x index in our tiles 2D array, effectively. So we do that for jump. We check both corners of his top of the top of his head. We do the same thing for the bottom, only that time we're checking x and then y plus height, and then x plus width, y plus height. And then if we're doing the left edge, what are we checking?
Bottom left and top left.
We are. So there'll be x0, y, and then x0, y plus height. And if it's the right edge, same thing. We check x plus width, y, and then we check x plus width, y plus height. And so that's the gist behind collision detection in the distro here. And you can see it in Mario if we go to his, if we go to Tilemap, point to tile, this is effectively where it happens. So notice that we are doing on line 32, basically returning this bit of code here, 28 to 30, is a check. Because we can jump over the map edge, we won't be able to check at tile y divided by tile size plus 1, x divided by tile size plus 1, because those will be nil. Those won't exist, because he'll literally be outside the map boundaries. Same thing if he like goes below it or he like goes beyond the left or right edge. So that's all this code is here. It just makes sure that if we do go beyond the map boundaries, we return nil, so that way we can check nil rather than getting a tile index error. And then on line 32 is the operation that I just mentioned, which was we take the y. So this x and y that we pass in are going to be the player's actual x, y. When we pass those in, we're just going to get the tile at self.tiles, and then effectively y divided by tile size taken down to an integer, and then add 1. Because recall, tables are 1 indexed. But pixels, the coordinates are 0 indexed. So this will result in a 0 indexed outcome. So we want to add 1 to it. Same thing for here. Math.floor x divided by tile size plus 1. So effectively, points to tiles. And then we'll just get a tile from that. And the tile, we can just check, hey, is that tile solid or not? If it is, trigger collision. So that's the gist behind being able to do it in a platformer where everything is fixed. That's sort of like a shortcut we can take. Because now, like, what's the nice thing about this? What jumps out as being like a super nice thing about this algorithm? Imagining that we have, let's say we have 10,000 tiles in our game world. So if you look and see, all we're doing is we're just doing a simple mathematical operation on what his x and y is, right? What's the alternative to this? Like if we were doing this via AABB, for example, we'd have to iterate over every single tile, right?
So sorry, can you summarize? To avoid iterating over everything on the screen, you just check the column that he's in and the column.
Yep. So the gist is he's got an x and a y.
Yeah.
The x and the y are going to be in world coordinates, so his x could be like 67 and his y could be like 38 or something like that. They don't map evenly to tiles, but if we divide those by whatever the tile size is in our world, 16, that's going to be the exact tile that, I mean, if we also have to add 1 to it because the tables in Lua are 1 indexed, but we can index our self.tiles at the x, y that we get from that, the dividing it by 16, and that'll be the exact tile that he's colliding with. And so we don't have to iterate over, we don't have to basically have a collection of tiles that we iterate over and check whether they collide with the player using AABB collision detection like we've done before. Because recall in Breakout, we had the bricks, right? They all had their own x, y, but they weren't on a grid. They weren't fixed. So we had to actually like take them and do an AABB. We had to iterate over them and perform AABB on them because there's no really deterministic way to just index at them really quickly. It's the same thing with like arrays versus linked lists. Like because arrays, you can calculate how far some value is given an index. You have instant access to it. It's a order of 1 operation. Or as opposed to a linked list, if you want to try and get to a particular value, you have to iterate through the entire thing until you find it.
You just look for the column that you might be colliding with.
You look for you're getting the exact tile at whatever your x divided by 16 or whatever your tile size is, and your y divided by 16 is. And you're doing it, recall, for 2 different points depending on what you're looking for. If you're looking for the tiles that are above your character, you're going to be doing it for this point. So whatever this value is, his base xy, whatever that is divided by 16, and then whatever that is divided by 16. And then that'll get you whatever tiles are directly above them, right? It'll intersect with whatever tile intersects with this point and whatever tile intersects with this point. Same thing with here and here if we're looking on the left, here if we're looking on the bottom, and here if we're looking on the right side. And this is done, we check for collision after he's already moved so that these points will be intersected with potential blocks. And that's how we can check whether it's a collision or not. We do this when he moves and is in some sort of movement state. Is that?
Still doing collision detection with his actual coordinates, but you're just narrowing like what you're comparing it with.
Yep. We're turning it from a iterating over every single tile to an instant operation, because we can just mathematically get the exact tiles that he's at without having to worry about where he is in the map. It's just instant access. And this only works because we know the tiles are always fixed in the exact same locations. They're always starting at 0, 0. They're always going to be tile size. Things get a little more complicated when we introduce game objects, which have their own independent x, y. And for those, you do have to iterate over. You have basically a collection of game objects or a collection of entities. Like let's say we have snails in the game world. The snails aren't going to be at some fixed location every time. They can move continuously. So for those, we have to actually keep them all in a container and then loop through them and say, has my player interacted or collided with any of these? If he has, then trigger a collision with that snail. Kill it, or kill the player if he's like in a walking state or a jump state. And if he's in a falling state, then they should die because he's colliding with them from the top, right? And you can you narrow down what collision you check for, as you can see at the bottom here. Tile collision, when you're looking above your character, you're only testing that when you're in the jumping state, because that's the only time you need to. So that's the only point at which you'll collide with tiles that are above you. When you're in the falling state is when you'll check for tiles below you. And then you can interact with tiles to your side when you're in either the jumping, falling, or moving state. So you should check for left and right tiles in all three of those states. Yeah?
Shouldn't you always test for beneath you in case you get a chasm?
In case what?
In case you get a chasm.
In case you get chasm. Yes. In walking, did I? Oh, you're correct. This should actually be tested only when in the player falling state and player walking state. Yes. So he said the question was, shouldn't you be testing for tiles beneath you when you're walking? And yes, not falling, not just falling, but walking as well. This one only jumping, this one falling and walking, and this one for jumping, falling, and moving. So. Does that make sense? How we can take the x, y and sort of turn that into a tile by just dividing it by 16? And do note the +1 as well, because our tiles in our self.tiles are 1 indexed. And so when we divide the xy by tile size, we're going to get a 0 indexed coordinate. Like if we're at tile, like if our x is at like 14, right? We're within the first tile. But if we divide that by 16, we're going to get 0. So we need to add 1 to that so that we get the first tile in the array still, which will be whatever that tile is. So that's sort of like how the collision works. It's all implemented in Tilemap here. So, and then every player, basically every state that the player is in, which is in states, entity, and then player falling, idle, jump, and walking. These are all states that perform this check. They check to see, they basically do all the logic that's here at the bottom, which is testing in the player jumping state, falling state, and moving state for left or right collision. And then in the falling state, we check for collision below us, and then jumping state, we check for collision above us. That's all done within the states themselves. But the actual transformation from pixels to tiles, that takes place, that's just a function that we call from Tilemap. It's just a utility function. So yeah.
What's the function called?
It's called point to tile. So if you're in Tilemap on line 27, point to tile XY, and the first little bit here is just the bit that lets you basically go outside the map bounds without getting a tile index error. So if it's just outside the tile limits, less than 0 or greater than width, just return nil. And so you can do a check on nil to check to see whether Tilemap point to tile is equal to nil or not when you do the collision. And if it is, then just don't do anything probably. But But on line 32, assuming that you're within the tile boundaries, on line 32 is where you do that transformation. The math.floor, recall, because we want to get integer values for these. We don't want to get fractional numbers because you can't index these tiles at fractional numbers. Although I'm not sure, I think you might be able to in Lua generally index a tile via a fractional number, but in this case, we just want integers. So we call math.floor on y divided by tile size plus 1, y divided by tile size, and then add 1 to that, and then we do the same thing for the x. So that's the operation. And then wherever we want to check for whatever tiles we want to collide for, we just call point to tile on those x and y coordinates. And that's the backbone behind all the tile-based collision in the game, effectively. Any questions as to how this works? Yes?
So you're only detecting the collision of corners and not the edge itself?
Correct, yeah. Because you don't really need to check for the edge if you're taking into consideration the top and bottom corner, unless your entity is sufficiently tall that they need to check for more than 3 tiles. In this case, our entity is not more than 2 tiles tall, so we only need to check for his top left, top right, or top left, bottom left if we're doing a left collision, top right, bottom right if we're doing a right collision, and his top left, top right for top, and bottom left, bottom right for bottom. If you had an entity that was like 8 tiles tall, you need to check every single tile along his right side, which just means you need to iterate over his entire height divided by tile size, and then just offset the y that you're checking for each of those tiles. Does that make sense? Okay, cool. All right, I alluded to this briefly by mentioning state. The sort of well, I don't know if I alluded so much to the fact that we're using entities, but in this distro, we're introduced to the concept of entities. An entity can be almost anything you want it to be. In this game, in this distro, we're considering entities to basically be anything that's living or sentient, moving around, in this case the player or snails. Those are entities. And then they just are subsets of entity. An entity is a very abstract thing. You'll see it in a lot of game engines and a lot of sort of discussions about how to organize your game and how to engineer it. Unity is probably the most prominent sort of adopter of what's called the entity component system, whereby you have everything in your game, every single thing in your game is an entity, and then every entity is comprised of components, and these components ultimately drive your behavior. It's sort of like if you're familiar with composition over inheritance. If you've heard of this as like a software engineering thing, that's effectively the same paradigm. Like rather than inherit a bunch of different things to be your, like let's say you have a base monster class, and then you have like a goblin that's a subset of monster, so it inherits from monster, and then you have like a goblin warlord who inherits from goblin, and then you have like a ancient goblin warlord that inherits from that. Rather than have like this nested tree of like inheritance, you adopt composition, which means you take a base container, and then you fill it with different components that represent what the behavior of your object is. So if you have a monster, or if you have an entity, let's say you give it a monster component, and then maybe your monster component, maybe you also give it like an ancient component, so it's an ancient monster. Maybe you give it a goblin component, so then it's an ancient goblin or ancient monster goblin, and then you give it like a warlord component, so it's an ancient goblin monster warlord. So it has all the pieces that make it what it is, without you having to create this crazy chain of inheritance. That's effectively what the model of an entity component system is versus standard inheritance, like using that to drive the model of your problem. In this case, we're not going into crazy entity components, but I wanted to bring it up because Unity, which we will be covering in a few weeks, is entirely component-based. Everything you write in Unity is a component. And entities, whether they're in an entity component system or not, form the backbone of most large games. Like most games that have some complexity to them model most of the pieces within them as entities that have behaviors and do things. And so in this case, entities are our snails and our player, and then we separate from the tiles. When we do collision for that, we want to also check collision on every entity with the player. So we make sure that the player is collided with a snail in this case, because those are the only other entities that they can be. But you can have an arbitrary number of enemies if you want to. if you collide with an entity, so just a for loop, so for entity in pairs of entities, check collision. If you're in the jump state, then die. If you're in the fall state, kill it, etc. That's generally when you're doing most of your like entity-to-entity interaction stuff. Like that's generally how you'll model it. You'll just iterate over everything and then just like collide everything. Depending on what collides with what, you'll just collide everything with everything else and like process interactions that way. That's effectively how we do it. We have in the, I believe it's in game level, this maintains a reference to just a table full of entities, a table full of objects. Objects can be, we'll talk about that in a second, but like gems and blocks and bushes and stuff like that, and then a tile map. And then we just, for every entity, we just update it. And then every object, we update it. And for every object in objects, we render it as well. And then we render every entity. Like this is just sort of like basic how you would take a game world, populate it, and then process and update it. Just containers, tables that just maintain a bunch of references to everything and then just update them. The actual interaction takes place in the, because they're dependent on what state we're in. If you look at all of the different states in the player class, or sorry, all the different states for the player in the states/entity folder, you'll see, for example, on line 62 of the player falling state, like we're iterating over every object in like the level.objects, and notice we have a reference to, like the player has a reference to its level so that it can like access everything within it, and then within that level, all the objects are stored. So all it needs to do is just say, if the object collides with the player and the object is solid, then set our dy to 0, et cetera, et cetera. All this code's actually pretty easy to read through, so I would encourage you to take a look at it and just sort of understand how all the collision and stuff is working for, between the player, the objects, the blocks, and things like that. Things like blocks are solid, things like bushes are not solid. But that's the gist. Like have a collection of objects or entities, and then depending on what state you're in, like collide with some, and then depending on the state, like maybe that kills you, maybe that kills the enemy, maybe nothing happens, maybe you become invincible, maybe you like collide with a power-up game object, and that power-up triggers like your self.player.invincible is true, and then if self.player.invincible is true, then maybe you render him with like a rainbow animation, and then in any of the functions where he would collide and die with an enemy, he no longer dies, he just kills them. So that's just sort of like the gist behind how you would interact with objects and like how to process it. Game objects are different, like I said earlier. These are example of like some of the objects here. We can see the gems on the bottom left there are all in the distro. Like if you hit a block, and if we have a few minutes, I'll show you really quickly how that works. If you hit a block, you'll have a chance to spawn a gem. If you collect the gem, which means if you collide with that game object, increment your score by 10 or 100. These are all other objects that I didn't have any time to implement, but just off the gate, just as a mental exercise, how do you think we could implement like a ladder? Yeah.
No, go ahead.
You would just have a climb state, and if the player is touching a ladder and presses a certain key, they would enter the climb state, and that would cause them to go up.
Correct. So what Tani said was if they go onto a ladder, they should go into a climb state. And depending on whether they're in the climb state or not, if they press a button, they should go up or down. Yeah, you would, and then you would check, if they're at the top of the ladder, get off the climb state, like go into a walk state, right? Or if they're at the bottom of the ladder, go into a walk state. And that's just, another game object that you just collide with, and then you're just, it's a new state for you. Yes?
You may actually want to put them in a false state, because that way you have a ladder that doesn't actually go anywhere, it just gives you height. So you could use that to jump over a walk down.
Tani said was you could have the ability to jump off a ladder. Is that what you said? Yeah, the ability to jump off a ladder so that you can then use it as an obstacle. That's absolutely true. Actually, in the mock-up that we saw up here, it's super hard to see. I'll see if I can maybe zoom in on it here. And Mario, graphics, and then it's called full sheet. The whole entire sheet that I used for this lecture is called fullsheet.png. I don't know what that is. So if we zoom in really high here, we can see effectively, yeah, what you were alluding to, like right here, this little rope thing. I'm guessing for the sake of this mock-up, that's sort of what they were trying to illustrate. But you have a game object that lets you go into a climb state, whether it's a ladder or whether it's a rope. Yeah, just add a new state for the player. If they're in that climb state, then we have this new animation, which we saw in the sheet earlier, which is their back or their front, and then they just climb up it, and just update it if they're moving up or down the ladder, and then just give them the ability to jump off, and then when you get to the top or bottom, just get off. So a lot of and you could think of a lot of the same thing with a lot of these obstacles, like the spikes here. If you're jumping and you hit it, you should probably die. And so, you would check for if the object.id maybe is equal to spikes, or whether object.dot is lethal equals true. Same thing with this one. And then some obstacles are completely cosmetic, like this mushroom here is just, in the case of the distro, bushes and mushrooms and cacti and all those sorts of things are just completely cosmetic, so you can walk through them. They don't trigger collision, but they're rendered as game objects. They're not part of the tile grid, so they don't get applied. They don't get rendered with the, or they don't get processed in the same way as tiles. They're not stored in the YX. But yeah, so that's effectively sort of how we can start thinking about objects and how to give them behavior. Part of the assignment is going to be adding a flag. So this flag is in the sprite sheet. So what you'll do, and I'll touch on this at the end of the lecture here. We're getting close to it, but these keys here, actually, at the bottom right. So part of the assignment will be to, it's actually right here. So I'll go over it really quickly. So ensure the player always starts above solid land. So in this case, when James came up here and ran, you ran the first example. The very first time that we spawned the game, it generated a chasm right at the right where the player spawned at sort of x1, and so it just falls to his death if that happens. So just make sure that and probably just right off the gate. Anybody have any ideas as to what we could do to check to see if we're at solid land, assuming that we start at the player's default start is at x1. Yeah, what we probably want to do is look all the way down the column, right? Because we start at towards the top, but if we find that there's no tiles down there, it's just pure chasm, probably want to shift the player. And then random keys and locks. So this will be, let me open up Level Maker so we can see sort of what you'll be interacting with, because most of what you'll be doing actually is in Level Maker. Level Maker is what it does is it does a lot of what we did before with just math.random, and then it will insert into objects. So objects is a table here. It will insert a game object depending on some logic. So in this case, if we're generating a pillar, we have a chance to generate a bush on the pillar. So if math.random 8 is 1, in this case, we're already generating a pillar, so we have an additional chance that's on top of the chance to generate a pillar. So basically I think it's a 1 in 64 chance on that particular iteration to generate a pillar with a bush. You just add a new game object to objects. In this case, this is sort of the constructor for a game object. You give it an x, y with height, and then a frame. And then the frame is relative to whatever quad table matches the texture string here. So bushes is the texture, and so whatever quad in bushes you want to give it. In this case, we just gave it a random frame from that. And then a lot of the same logic applies to other parts. This is another part where we generate bushes just on flat land. We have a chance to generate a block, 1 in 10 chance. This is a jump block. So here we have texture, x, y with height, frame. Notice that we have collidable is true, and this is how we can sort of test to see whether a tile is collidable or not. Hit is false, meaning that we haven't hit it yet. And if we have hit it, then we want to, we do this code, basically. OnCollide gets called. And you can read this if you look in, you can see where this gets called in the collision code for, if we look in player, players. Player has check left collisions, check right collisions, and check object collisions. It doesn't have check up and down collisions. There was a corner case for both of those, such that the logic had to be duplicated. Forget exactly why, but you basically get a list of objects that you check for, and then the reason why is because when you get the collided objects when you're in the jump state, you trigger the onCollide function. So let's go to player jump state. If we're in the jump state, and this is where we basically check to see if we've gotten any objects that collide with the player. If it's solid, call its onCollide function, object onCollide, and then we just pass in the object itself, basically. And so if we go back to level maker, that's where we write the onCollide function. We write the onCollide function within the game object here. So we just give it an onCollide. Remember, because functions are first-class citizens, we can just say onCollide gets function obj, where obj is going to be this object. If it wasn't hit already, 1 in 5 chance to spawn a gem. So going to create a gem. It's got all the same sort of stuff. And on this case, it has its own function called onConsume. OnConsume takes a player and an object. And then this is all arbitrary, by the way. You can create whatever functions you want. These are callback functions, effectively. We're just going to play the pickup sound and then add 100 to our score. And then here, in the event that we did get a gem, we tween it over the course of 0.1 seconds. We tween its y to be from like below the block to up above. So it has like an upwards animation, effectively. And then we have another sound that plays. But that's effectively how we're spawning game objects. Game objects have textures, x, y, width, height, and then you can give them callback functions that you then execute wherever it's relevant to you. In this case, you'll only really need to worry about onCollide because the assignment is create random keys and locks. It can be, they have to be the same color, but you can choose them at random. If the player collides with the key, then he should probably get some flag that's like key obtained is true or something like that. And then you go to the block that spawns in the level. So you should spawn a block with that same color. And then onCollide, you should unlock it, so get rid of the block. And then spawn a new game object, the flag. And then that flag, he'll have its own onCollide. And when you collide with the flag, restart the level. And that's effectively the gist behind the problem set. So probably shouldn't take, I would say probably maybe 40 or 50 lines of code probably should do it. Yeah.
That game object, it's not a class or it's not a table. What is that?
It is a class. So here's,
Okay.
yeah, there's a game object class. A game object is basically, and I realize I didn't touch on it too much, is basically in the context of this distro, you could almost think of it as an entity. In this case, what I've done is I've differentiated between living things and non-living things as being entities versus game objects, which is a semi-arbitrary distinction. But for a small project like this, it sort of makes sense. For a large project, I would probably create everything as an entity and then give different kinds of entities their own behavior and their own components, sort of like you do with an entity component system.
Are there two ways to create a class in Lua? Like one with the curly brackets and one with just regular parentheses?
There is actually. You're talking. So the question was, is there more than one way to create a class in Lua, whether it's parentheses or curly brackets? And yes, I don't think I ever actually talked about this, but Lua allows you, if you generate. Here, let's go back to level maker. If you instantiate a class, and that class just takes in a table, just a table as its only argument, you can just pass in this. Whoops, sorry. This effectively is that argument table. You don't need parentheses. You can just, it's effectively doing this. Same thing, only you don't need the parentheses.
And then that's a table that's being passed in?
Correct.
And,
It's just an alternative form of instantiation on things that only take a table as their argument for when they get instantiated.
And you can only have one table in that case, right?
Correct.
Okay.
Yes. Yeah.
Wouldn't it be easier to create a new class which would have its own set of game objects? So you would create a gem which would be helper.gem, which would in turn create a game object?
Can you say it one more time?
It's kind of hard to explain. Wouldn't it be easier to create your own another class which would have your gem and everything, and your gem in that class would be a game object, but in this class when you wanted a gem you would say local gem equals helper class.gem?
The question was, if you wanted to, wouldn't it be easier to generate a helper, to create a helper class that would allow you to instantiate gems? Possibly. I think if you were going to design this a little bit more robustly, and if this were going to be a larger game, then you would just create a subclass for blocks, gems, etc., to shrink the number of files that we had in the distro and to sort of consolidate everything together and put all of the sort of level code together in one spot. I decided to just create game object as sort of like an abstract class that you could then just create your own behavior for within the actual constructor, which is this bit here, which is just the table, and then allow you to override the onCollide and onConsume functions. And you can actually give it whatever functions you want. You could give this some arbitrary named function and then test for it later. This is sort of almost like an obscure way of inheritance, but I think if I were to engineer this with the goal of making it a really large game, I would just subclass I would just create a class for gem, a class for block, a class for bush, et cetera, et cetera. It wasn't strictly necessary for this example, so we ended up keeping everything a little bit more sort of abstract, I guess, in this sense, a little bit more general purpose. But yeah, you could definitely create classes for those. And if you were an entity component system, you could have like a consumable component, and then that consumable component would then allow you to give it some sort of behavior that affects the player when the player consumes that object. In this case, a gem is a consumable, so you would just give it a consumable component with a texture of the gem, and then give that function, give it a callback function that just increments the player's score, and probably put that in like 10 or 15 lines of code. Be pretty easy. And then blocks would be like a spawner component, so they have a chance to spawn, and then you would pass in that spawner component like a gem maybe, and then so it would spawn that, have a chance to spawn the gem that you pass into the spawner component, and then also like a collidable like a solid component to say, oh, this is solid, so if I hit it I should like trigger a collision and not be able to walk through it. So you just sort of layer on these components. I would encourage you to sort of think about this way of composing your objects a little bit, particularly as we get towards Unity, which makes really sort of a lot of use of this concept. But yeah, in short, yes. I think that's pretty much everything. Let me just go ahead. We're running out of time here, but like I said, one more time, make sure the player starts above solid land, random color, key, and lock, and then make sure that when you get the key, you can unlock the lock, and that spawns the goal. So this is all something you can just add to your level maker, the level maker class, and that'll just sort of it'll all sort of work with your game level that way. And then when you touch the goal flag, then respawn the level. So next time, today we talked about Super Mario Brothers, the other big Nintendo game of that era, arguably one of the greatest of all time, is Zelda. So we'll be talking about a very simple sort of Legend of Zelda game where we just have like a random dungeon that we can go through, a top-down perspective, fight simple monsters, open chests, blow up walls, that sort of thing. We'll talk about triggers and events, and then we'll talk about hurt boxes, inventory, a very simple GUI for like opening up a menu, and then world state so that we can see, which doors have been blasted open so that they render appropriately and whatnot. And that's it for Mario. So thanks a lot for coming. I'll see you guys next time.